to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello students, I hope you are okay. I want to take this time to welcome you to our TV lessons. And today, as usual, we are going to learn Senior 2 Physics, Unit 4, which is Density and Pressure in Solids and Fluids. And specifically this lesson, we shall be dealing with atmospheric pressure. My name is Teacher John Bosco, and as I've been telling you, you can call me JB. And so I hope you will enjoy this lesson for the next 30 minutes or so. So, to begin with, if you remember last time we were looking at atmospheric pressure, okay? Atmospheric pressure. One of the questions that I asked you, I hope you still remember the question, you may have done it already, was that you were supposed to define the term atmosphere and atmospheric pressure. Do you remember what we said about atmospheric pressure last time? Yes. Atmospheric pressure is the pressure exerted by the weight of the gases in the atmosphere. It acts on all of us, on all objects that are on the surface of the earth. And so, last time, there were many experiments that we did to demonstrate atmospheric pressure. Do you still remember those experiments that we did? I just want to remind you of one of those experiments that we did last time. I hope you tried it. Remember what we did was one of the experiments, we filled up a test tube with water. It could be any container, doesn't necessarily need to be a test tube. You just fill it up with water and then get a paper, put the paper on the test tube, and using one hand, you put your hand on top of the test tube and turn it upside down. You can see that the paper holds the weight of the water inside. It's kind of magical. You know, why does the paper hold the weight of the water? It is because of atmospheric pressure. And so today, we want to continue looking at applications of atmospheric pressure. How do we use it in our daily lives? There are actually very many applications of atmospheric pressure. But today we shall look at only two. You can continue investigating about other applications of atmospheric pressure, looking at your physics book for Rwanda schools, book 2. Look at so many of those applications they are explained there. You can even research on the internet and find so many other applications of atmospheric pressure. So today, as I told you, we want to look at only two of them. The first one is the drinking straw. Have you ever used a drinking straw? I believe so. This morning I used a drinking straw. I was taking a bottle of juice. Very many of us use drinking straws. So if you're using a drinking straw, you should know that you are actually using atmospheric pressure to allow you to drink. So let us look at this diagram that we have on the board. Very wonderful diagram. This is a straw. I hope you can see it. And this is soda. It could be juice. It could be water. And this is a glass. So if you're going to drink using a straw, you put the straw in the juice or in the soda. And once you do that, some water or some soda or juice will enter inside the drinking straw. Let me mark the level of the soda in the straw. It may rise up to this level. And so, when you put your mouth at the end of this straw, what is found inside here? Inside the straw. Remember, there's no soda there. But there's something found inside the straw. Do you know what it is? Yes, someone says air. Good. There's some air inside. And so when you are going to drink, you first begin by sucking. You begin by sucking. That is taking in the air inside your mouth. That's what we begin with. So when you take in air inside the mouth, it means this space would remain like a vacuum. And if it is a vacuum, what does it mean? Outside here, we have got atmospheric what? Atmospheric pressure outside, which is pushing the liquid surface downwards. But inside the straw, there's no pressure because you have taken the air which was inside. So are we going to have a pressure difference? Yes. Outside there is more pressure, but inside there is very little pressure. And therefore, the liquid is going to be forced to enter inside the straw where there is little what? Where there is little pressure. And so the liquid will begin rising in the straw and it will enter your mouth so you can drink it very easily, almost effortlessly. So that is how atmospheric pressure helps you to drink a liquid using a drinking straw. Isn't that wonderful? A very wonderful application of atmospheric pressure that all of us get to do perhaps on a daily basis. Then, the second one is very interesting. Very interesting. The second application today is called the siphon. Maybe you are listening to this word for the first time. The siphon. Looks like a big word, but it isn't. The siphon. So, how do we use this idea of the siphon in our daily lives? We can apply it like if you are driving a car or your parent or your elder brother is driving a car, you happen to be in the car, and then fuel gets finished. But then there's another car which has got some fuel, and you want to remove fuel from one car to the next car. You are not at a fuel station, remember? How then do we remove fuel from the tank of one car to the next one so that you can continue with your journey? We then use a siphon. And in a siphon, we are going to demonstrate it using two containers. Okay? So you have this container, which I'm calling a tank. It has some water. Then the second container that I'm calling a basin, it doesn't have water. I must also have a flexible rubber tube. That means a piece of rubber that is flexible. You see like this one? This is a flexible rubber tube. I was not able to get this, but I'm going to use this. This is a flexible rubber tube. So for our case here, this is going to be our basin, and this is going to be our tank. We shall then want to use the idea of the siphon to remove water from this tank or from this beaker into this basin. So what is the physics behind? The physics behind, remember, we are using the idea of atmospheric what? Atmospheric pressure. And so, when you come to this, you see that this liquid surface is exposed. And so there's a pressure which is acting downwards. And this pressure is what is referred to as atmospheric what? Atmospheric pressure. It is pushing it downwards. But is it able to push this liquid and the liquid goes against the force of gravity? This is quite very interesting. Look at this area. Look at this. How do we make sure that water moves up against the force of gravity? Because if you have water, water will pour going down because force of gravity is pulling it towards the center of the earth. How then do we make it move up? Very interesting. Let us watch this demonstration, which you can do, by the way, at home very easily and see whether that can happen. So what I'm going to do, you see, there's no water in this tube. No water. So I'm going to push this tube. I hope you can see very well. We are going to push the tube into the beaker, and we want to see whether water can move up like this against the force of gravity. Is that possible? That's what we want to see. So I'm going to begin. I will suck water into this tube until the water reaches my mouth. Of course, you must do it with clean water. And this is clean water. If you do it with dirty water, you could get some infections. So if you are performing this experiment, make sure the water is clean and the tube is also very clean. In my case, they are quite clean. And so I'm going to suck it until water reaches my mouth. The moment water reaches my mouth, I'm going to hold the tube and put it in the basin. You remember in our diagram we are talking about the basin? And see whether water can be forced to move against the force of gravity. Okay, let us observe carefully. Here we go. Right? I sucked water, it reached my mouth, and I left sucking. I stopped sucking. And you can see what is happening. Do you see the level of water in the beaker? Is it reducing? Is it reducing? To me, it is reducing because we started when the beaker was full. Now look at where the level of water is. And as you can see, you can imagine water climbing up against the force of gravity. I think that is wonderful. Water is moving up the force of gravity and against the force of gravity and coming into this container. So this idea of application of atmospheric pressure is called the siphon. And so, as we said before, what is the application of this? You can apply this in a car. If I want to remove fuel from the car and put it in a jerry can, so I can transfer this fuel into another car, I can use the idea of the siphon very easily. And it works on the same principle as a drinking straw, as we said before. So that is a wonderful application of atmospheric pressure that I believe you guys have followed. And you can demonstrate this at home. When you go back to school, you can ask your physics teacher to avail you with this equipment, with the apparatus, then you can also perform it at school. Very interesting. Good. The next idea we want to look at, still on atmospheric pressure, is measurement of atmospheric pressure. Remember, we said atmospheric pressure is a pressure exerted by the weight of the gases in the atmosphere. So what does it mean? It means that atmospheric pressure, many times we abbreviate it like this, P, then ATM. This is just a short form for atmospheric pressure. Instead of writing the whole word, I can write this. So atmospheric pressure can also be measured in newtons per meter squared, just like any other pressure. We can also measure it in Pascal, just like any other pressure. So how can we tell the value of atmospheric pressure in a place? That is what we want to look at. Measurement of atmospheric pressure. Now, the instrument used for measuring atmospheric pressure is referred to as can you read that word? Yes. Let's read it together. The instrument used for measuring atmospheric pressure is called a barometer. You see? Barometer. Now, how is a barometer constructed? It's quite easy to understand how it is constructed. And right here, I'm just going to demonstrate to you the processes that lead to the construction of a barometer. Okay? I want you to observe it well because it is this idea that we shall use to explain how a barometer works. So I'm going to pour some water in this test tube. You can see it is full. I will put one finger on the mouth of the test tube, and then I will turn it upside down and introduce it into the water, which is in our Petri dish. Now, look at that. All this is made of, it's full of water. The water is not coming out into the Petri dish. Why? It is because atmospheric pressure is pushing the surface of this water, and it is able to maintain this level of water, this height of water, a lot of water in the test tube. And look, the test tube is full. If I did this with another test tube which is longer, it would support even a greater height. It supports a height of even more than 1 meter, even more than 2 meters. It supports a height of more than 10 meters. It means atmospheric pressure is very strong, is very powerful, because it can sustain, it can support greater heights of water. And that also because water is having a low density. If we used another liquid with a high density, like mercury, by the way, from your senior 1, when you are looking at densities of different substances, or even senior 2, you should remember that the density, which is written like this, of mercury, is about 13,600 kilograms per meters cubed. That's the density of mercury. But what about density of water? Density of water is about 1,000 kilograms per meters cubed. Do you remember it? You should remember that. So if we use water, the height which can be supported is very high because the density is low. What about if we use mercury? Will it support a very great height? Okay, let us see. So we repeat the same experiment like we did here, but we don't use water. We now use mercury. Unfortunately, I don't have mercury here, so we shall just look at what happens when we use mercury. So if we use mercury, atmospheric pressure will push this surface down. This is atmospheric pressure, causing the mercury to rise in the test tube. But it will only rise to a certain height, and there's going to be an empty space above the mercury. What do you call an empty space without anything? Vacuum. Good. Vacuum is a space without anything. So above this mercury, we are going to have a vacuum. And if you measure using a meter rule, as you're doing your experiment, if we measure the height, the distance from the height, the level of the liquid in the dish up to where the liquid is in the test tube, I mean measuring such a distance, if you perform the experiment, you see the distance we are talking about from the level of water there, or level of liquid, up to where the vacuum starts. Unfortunately, this one doesn't have a vacuum, of course. So that would become the height. So if you do that for this experiment, and the experiment is done at sea level. When I say it is done at sea level, it means it is done at the level of the sea. Like, you see this diagram here? This is like a cross-section from the ocean to inland. And I've put some cities here that we shall talk about very briefly, maybe in 1 or 2 minutes. But if you perform your experiment at the sea level, the other experiment at sea level, you will find that this height is going to be 760 millimeters. Okay? 760 millimeters. If you want to change that into centimeters, it will be, you divide this by 10. That becomes 76 centimeters. Again, if you want to express it in meters, we divide this one by 100. That becomes 0.76 meters. Do you see that? That is the level of the mercury. The distance from the mercury surface in the Petri dish here up to the upper meniscus. That means the uppermost level of this mercury. We find it is equal to 760 millimeters. I hope you get that. And that is very fundamental, very important. For some of you who will do courses in aviation, maybe at the university, and other related courses, you need to understand very well the idea of atmospheric pressure. If you are going to fly a plane, you need to know the pressure at the heights where you are going to fly your plane, because the turbulence can easily affect how a plane moves in the sky. And that knowledge of atmospheric pressure is very important. And so this 760 millimeters is called the standard atmospheric pressure. Okay? We call it standard atmospheric pressure. And the standard atmospheric pressure is equal to 760. We talk about the height, but the liquid we are using there is called mercury. So we call it 760, we say 760 millimeters of what? Of mercury. And that is the standard atmospheric pressure. 760 millimeters of mercury. So you need to get that point. And so if we do the experiment, again you focus on this wonderful diagram. If we do our experiment at the sea level, it means the standard atmospheric pressure is going to be 760 millimeters of mercury. But atmospheric pressure depends on altitude. As you go higher, the atmospheric pressure reduces. The higher you go, the lower the atmospheric pressure. So when you look at cities like Mombasa in Kenya, this is at the sea level. Atmospheric pressure is 760 millimeters of mercury. When you come to a city like Nairobi, it is higher than Mombasa. Do we expect the atmospheric pressure to be 760? No, it should be less. If you come to a city like Kampala, I'm picking major cities of East Africa. If you come to a place like Kampala, it is lower than Nairobi. So the atmospheric pressure in Kampala is not the same as that in Nairobi. Look at the height. Nairobi, the height is 1,795. Kampala, 1,200. In Kigali, it is about 1,200, slightly higher than that. So atmospheric pressure depends on the height. And as you can see, we have already seen that the unit of atmospheric pressure is, unit of pressure is newtons per meter squared. But we also have other units, like Pascal. Today, we shall see that there are many more units of atmospheric pressure that is widely used. Let us see some of them. I hope you can see this. What is this one? PA. Remember, it stands for Pascal. What about this one? Newton per meter squared. What about this one? Millimeters. In chemistry, Hg is the chemical symbol for mercury. So this is millimeters of mercury. Remember, that's what we have just seen right now? It is here. Millimeters of mercury. So it means millimeters of mercury is another unit of atmospheric pressure. Then we have atmosphere. Isn't that puzzling? How can atmosphere be a unit? But it is a unit. We shall see what it means. Then we have bars. Then we have torr. You see? So today we have seen there are so many units that we can use to express atmospheric pressure. Pascal, newtons per meter squared, millimeters of mercury, atmosphere, bars, and torr. So the last thing we want to look at is the relationship between millimeters of mercury and Pascal, and newtons per meter squared. That's the only thing we want to look at today, then we shall conclude. So we are converting from millimeters of mercury to Pascal. That's what we want to do. Pressure is given as rho GH. Do you remember that formula? Yes. And so, rho, because here we are using mercury, so this is going to be density of mercury, which is 13,600 times G. What's the value of G again? The value of G is 10. So we are going to multiply this by 10 times H. Standard atmospheric pressure, look at its value. It is 760. So we have 760 millimeters. But millimeters is not standard. We need to convert it into a standard unit. So we change it into meters. That means we divide this one by what? 1,000. And when you divide this by 1,000 and you compute, we are going to come out with 103. Please try to compute this also. 103, 360. That's what you are going to get. 103,360 Newton per meter squared. We can also say 103,360 Pascal. Because remember, 1 Pascal is equal to 1 Newton per meter squared. And so, in the next topic, we will continue investigating, in our next lesson, we'll continue investigating the relationship between atmosphere and a bar, atmosphere and millimeters of mercury, atmosphere and Pascal, bar and torr and millimeters of mercury. That's what we are going to discuss in our next topic. So, as we summarize, our objective today was for you to know some applications of atmospheric pressure, which we looked at in the siphon and in the drinking straw. We have also seen that atmospheric pressure depends on altitude. As you go higher, atmospheric pressure reduces. And also, we looked at the instrument to measure atmospheric pressure, which is the barometer. And that is how a barometer works. And so I'm going to leave you with a simple assignment, which you can present next time. And the assignment we have I want you to convert 700 millimeters of mercury into Pascal. Then 2, I want you to convert it into newtons per meter squared, which you can write as Nm to power negative 2. How do you convert those units of pressure? Converting 700 millimeters of mercury into Pascal and 700 millimeters of mercury into newtons per meter squared. So as I told you, in the next lesson, we shall be able to see the relationship between millimeters of mercury and other units of pressure. So I want to thank you again for being good students, good listening students. I hope you have been taking your notes and you are going to continue investigating more information about our lesson today, and we'll meet next time. Thank you.